In this video, we will cover the basics of scanning electron microscopy, or SEM. With SEM, one is able to obtain magnification over 250,000 times the sample size, allowing resolutions of the order of 1 nanometer. At the heart of every SEM instrument is the electron beam source, typically called an electron gun. A series of lenses after the electron gun are used to focus the electron beam into a much narrower diameter. These electron microscope lenses are magnetic fields, unlike the glass or plastic lenses of optical equipment. The electron beam also passes through apertures which block the path of any electrons unaligned with the aperture opening. If the aperture diameter is smaller than the electron beam, it will narrow the beam but will also reduce the total number of electrons that reach the sample, thereby decreasing the brightness and signal-to-noise ratio and increasing the depth of field, or amount of the sample that appears in focus. The condenser lenses and aperture primarily determine the beam diameter, whereas the objective lens ensures that the electron beam is focused so that the electron paths all converge to the same point as close to the sample surface as possible. If the electron beams converge above or below the sample, it will appear out of focus. Unlike optical lenses, these electron lenses can be dynamically adjusted by varying the DC current in the electromagnets that make up each lens. A final set of coils is used to deflect the beam so that it can be raster scanned across the sample. In other words, the electron beam will be focused on this point until a measurement is made, and then it will move here, and then here, and then so on until an image is produced. There are many ways in which the incident electron beam can interact with the sample, including scattering, absorption, transmission, diffraction, and photon emission. A typical SEM instrument will not have equipment to detect all of these interactions, and transmitted and diffracted electrons are not considered part of an SEM experiment. The remaining interactions all convey different information about the sample. Secondary electrons are electrons that have been ejected from the sample due to an inelastic collision with an electron from the incident beam. These secondary electrons typically have energies less than 50 electron volts, so if they originate from an atom too deep within the sample, they will not have sufficient energy to leave the sample and be detected. If the emitted secondary electron came from a core shell of an atom, then an outer electron from that atom would relax and emit energy to assume the inner core vacancy. The energy is released in the form of an X-ray photon and is closely tied to the identity of the atom from which it came, so detection of these X-rays offers elemental analysis for the sample. The incident electrons can also collide elastically with the protons of the sample. These backscattered electrons typically have energies close to that of the incident beam, but can have lower energies if they also collided inelastically with the sample. As such, they can be distinguished from the secondary electrons. The frequency of backscattered electron emission is directly related to the size of the nuclei in the atoms of the sample, allowing backscattered electron detection to provide both compositional and topological information about the sample. The secondary electrons are attracted to a charged screen in front of the detector, so the emitted electrons do not have to be ejected directly toward the detector in order to be measured. However, portions of the sample closest to the detector are likely to have more detected secondary electrons than those farther from the detector, or those that are blocked by the topology of the sample surface. This leads to an image with brighter features near the detector or near the edges of a sample. This can be a limitation of SEM, since some topological features of the sample may be lost due to shadowing. It is common to represent these electron interactions with what is known as an interaction volume. In essence, if an electron interaction can be detected from a greater depth within the sample, then the spatial resolution of the surface is decreased. For example, secondary electrons cannot be detected far from the surface of the sample, but the X-rays from these interactions can be detected. Even if the electron beam is focused on this section of the sample, collisions of the beam electrons with the sample can cause interactions outside this region, especially if the beam energy is high. Therefore, a beam focused on this section of the sample obtains information from this section of the sample. Therefore, secondary electron detection offers the best topological information for the sample. Backscattered electron detection offers less spatial resolution but provides information about the composition of the sample. X-ray detection provides no topological imagery, but provides decent spatial resolution of the composition of the sample. SEM imaging requires high vacuum, which inherently limits the properties of the sample to be imaged. Liquid samples or solid samples with entrained liquids, such as biological samples, cannot be imaged with traditional SEM. Furthermore, traditional SEM requires that the sample be conductive. Otherwise, the incident electrons can build up a charge on the sample, causing artifacts or distortions in the resulting image. If a non-conducting sample is to be imaged with SEM, it must be first coated in a conductive layer, which is typically gold. The quality and thickness of the deposited layer has a large impact on the resolution of the topological data and can interfere with compositional analysis from backscattered electron and X-ray detection. This modification also destroys the original identity of the sample and will likely interfere with subsequent analysis techniques. A newer technique known as environmental SEM overcomes these limitations by partitioning the electron gun and lenses in the column from the sample, and by accounting for electron interactions with gaseous vapors in the sample area.